Welcome to video number 2 of me relearning Maxwell's equations by doing the homework in the book A Student's Guide to Maxwell's Equations by Daniel Flesch. Okay, here's the problem I wanted to do. 1.6. I should have been capital. A 10 centimeter by 10 centimeter flat plate is located 5 centimeters away from a point charge of this number. What is the electric flux through the plate due to the point charge? Now, this isn't really a math problem as much as it is a logic the problem. And what's fun about this book is that everything you need to solve these problems is in the chapter before the problems are listed. You just got to put the pieces of the puzzle together. And this puzzle was realizing, and he explains this in the book, this is a point charge, so it's generating an electric field, and that electric field is generating in all directions, right? It's not just generating toward that. He drew this plate. That should be a square, but it's obviously doesn't look like a square. But you know what he meant. So if that point charge is in the middle of a cube with these dimensions, so each side is 10 by 10, then how do you calculate the electric flux due to just one side of that cube? All right. So the electric field is radiating everywhere. And since this box now has 6 sides, right? It has 4 sides and a top and a bottom. Then the flux through one side is just 1/6 of the total flux. That's all he wanted you to do. So that was kind of fun. So he gave you the total charge, and you know this constant, so you calculate the total flux, divide it by 6, and boom. That's all. That's all that was needed. Okay, now there are several more the problems that are similar to this, but they're basically all the same, so it got boring. So I wanted to skip to something that's not boring. But before I do a problem, we really have to talk about what's in the book, because if you don't have the book, this won't make any sense if I just jump into the problem. So he's calling this a special Gaussian the surface. And what he's explaining here is that you have some kind of charge inside of a sphere. And you know that when they show electric fields or any field, they always show them as vectors, right? But in actuality, there's an infinite number of vectors here, right? They're all radiating in the same direction. And if you enclose that in a sphere, he's calling this surface the special Gaussian the surface, which is showing that everywhere there's an electric field emerging from the surface, that the unit normal, the vector, is parallel to that. So that's how he's defining a special Gaussian the surface, where every part of this, in this case, because it's a sphere, the unit normal is parallel to the emerging electric field lines. Okay, so when we take the integral form of Gauss's law like this, and we look at this the field inner product with the unit normal, we can write the definition of a product, the magnitude of E times the magnitude of the unit vector times the cosine angle between them. Well, we know what the magnitude of this is. It's 1 by definition. And the angle between them is 0 because they're parallel. So this goes to 1. So this E1 times 1. So it's just the magnitude of E, right? So if we put that back into our equation, now this just becomes a scalar. We can pull it out like this. Well, now what's this? Well, this is the infinitesimal area for a sphere. How do we find that? Well, the only way I could figure it out was that dA is equal to the derivative of the volume of a sphere with respect to the radius. And we know what the volume is. A sphere is. It's 4/3 pi r cubed. We take the first derivative with respect to r, we get 4 pi r squared. So this is the dA of our surface, okay? So we put that back in here. We solve for E, which is now just a scalar. And so you get this equation, which relates the magnitude of the field to the radius and the charge enclosed in this format. So that's what all of this section is about, the special Gaussian the surface. And the reason I wanted to do that is because of the problem we're getting ready to do. Okay, here's the problem as given. Use a special Gaussian the surface around an infinite line charge to find the electric field of the line charge as a function of distance. So like I said before, every problem in this book, somewhere in the chapter before it, you can find how to do it. And I dug and I dug and I dug. And as soon as I saw this drawing he had in the chapter, I knew what I wanted to do. Okay. So this is a cylinder, a closed cylinder, by the way. So if passing through this was an infinite line charge, right? Then think about this. The electric field emanating from that line is going in all directions, in these directions, right? So you can see that you have unit normals parallel to that electric field, but you have some unit normals, mainly the ones on the top and bottom, that are perpendicular to the electric field because they're going this way. Imagine there's a line going right through this whole thing, and it's emanating an the field. So that was the key to solving this problem, was finding this drawing in the chapter. Okay, so we write this equation down, and we just said that the electric field component here has two parts. It has a parallel part and it has a perpendicular part. Well, the parallel part, we just did that, and we know it's just equal to E. Now, what's the perpendicular part? Well, the difference is that the cosine of the angle between the electric field part and the normal is 90 degrees. What's the cosine of 90? 0. So this drops out, so we don't need it. Okay? So now we can pull our E outside our integral just like we did. Now, once again, we have a dA here. What is the dA of a cylinder? Well, I found this little drawing on the internet, which I borrowed. And the surface area of a cylinder has two parts. So it has the ends, top and bottom, and it has the sides, right? So this disk here on the bottom is just pi r squared, and there's two of them, one on top, one on the bottom. So there's just two of those. Well, what's the other part? What's this part in here? Well, I did it the same way I did the sphere, is I said, what is the volume of a cylinder? Well, from 0 to h of this pi r squared, you just integrate up over h, you get pi r squared h. You know, it was that easy. Well, then if that's true, then what's dA? Well, it's just the first derivative of that with respect to r. So this is the other part, 2 pi rh. So dA is equal to this. But we just said the electric field on both ends is 0, so we don't need this part because there's no electric field there, 0. We just need this part, right? So we plug that in here, and we get this equation. We solve for E. The cat jumped on me, sorry. And here is what so this is the answer, but that's not what he wanted. The way he worded this was as a function of distance, right? So we don't have any distance in here yet except r. So back in the book, equation 1.112 is the total enclosed charge is equal to the line, the density times the length of that line, right? So when we were doing the problems in the last video, we had this as a line density, as an area density, and a volume density. Well, this is just the one with the line, the density. So he actually wants this to be here. So you plug that in, and you realize that h is just L. It's just the length of the cylinder. It's the same thing as the height of the cylinder. The L's will cancel, and this is the answer he was looking for. Okay? So, and most of the ones in the rest of the problems in this chapter are exactly similar to this. I don't see any point in doing them because because now we have an idea. So we're going to jump in. The next video is going to be the differential form of Gauss's law. All right. Well, thanks for watching.